Imagine writing a complex piece of software and having absolute mathematical certainty that it contains zero bugs. I mean, no testing loops, no crossing your fingers before deployment, just pure verified logic. Or imagine a pixel on your screen that is not just showing you an image, but is simultaneously looking right back at you as a microscopic sensor.
Welcome to episode 558 of AI Brief. We have an extraordinary deep dive for you today. We are looking at Mistral turning formal verification into an absolute open model arms race. We are tracking massive scientific breakthroughs, including lab-made cells and boundary-pushing hardware. And we'll finish up with a rundown of the top trending AI tools that you can use to immediately boost your productivity.
Today is fundamentally all about blueprints. We are exploring models that can formally prove software code mapping the underlying logic of our digital world, all the way down to scientists who are quite literally rewriting the basic blueprints of biology and human interfaces. So we are diving straight into our new updates today, focusing on Mistral's aggressive new play with Mistral 1.5. This development, it completely redefines what we expect from open source models. They've released an Apache 2.0 model, which means it is entirely open and permissible for commercial use. It boasts 119 billion total parameters, but here is the fascinating part. It operates with a highly efficient 6 billion active parameters during inference.
That architecture is crucial for you to understand. Having 119 billion total parameters means the model has this massive reservoir of knowledge, but only activating 6 billion at a time. That means it runs incredibly fast and cheap.
Wow.
It pulls only the specific expertise it needs for a given prompt, rather than lighting up the entire neural network every single time.
That efficiency makes the benchmark scores even more staggering. I mean, Mistral 1.5 hits 100% on Mini-F2F, which is a rigorous benchmark for mathematical reasoning, and it solves 580 out of 672 Putnam bench problems. For context, Putnam problems are notoriously difficult math challenges that stump top university students.
Oh, absolutely.
And it also achieves state-of-the-art results on FADE-H and FADE-X, which are specialized benchmarks for formal verification. To give you a sense of what this means for your operating budget, evaluating Putnam bench problems using proprietary models costs around $4 per single problem, just one math problem.
That is wild.
The Mistral 1.5 acts like a brilliant, dirt-cheap PhD mathematician on call to solve your most complex logic problems, costing a fraction of what you would pay for much higher-cost competitors.
The cost reduction is a total paradigm shift. Formal verification, which is the process of mathematically proving that a program's code matches its design specifications, has historically been a niche specialist battlefield. It was restricted to expensive proprietary systems, usually reserved for aerospace or nuclear software where bugs are catastrophic.
Sure.
So bringing this capability to an open model at a low computational cost completely democratizes that level of security.
And the training pipeline reveals exactly how they achieve this. Mistral utilized mid-training, supervised fine-tuning, and something called reinforcement learning with CISPO. For those who might not be deep in the weeds of model training, CISPO is essentially a specialized mechanism that trains the model to double-check its own logic.
Which is so important.
It ensures the math actually holds up, rather than the model just generating code that looks superficially correct. They also heavily utilized agentic environments, allowing the model to iterate directly on lean compiler feedback.
The lean compiler is effectively a ruthless, automated math teacher. When the model writes a proof for a piece of code, the lean compiler grades it with absolute strictness.
Wait, so it just rejects it instantly?
Well, yes, instantly. By using agentic environments, Mistral allowed the model to submit an answer, get rejected by the compiler if there was an error, and autonomously rewrite the code until the compiler accepted it. The model learns through continuous, brutal trial and error during training.
And the real-world impact of that brutal training is already here. In code verification tests run across 57 different open-source repositories, this specific pipeline found 11 real bugs. The standout detail is that 5 of those were previously unknown GitHub issues.
Unbelievable.
An open model found deeply hidden flaws in human-written code that no one else had spotted. You can find Mistral 1.5 available right now on Hugging Face, and Mistral has provided a free API endpoint called Mistral 1.5 to let developers experiment immediately. Oh, and there's also a highly entertaining subplot surrounding this release, the Le Chiton Fat saga.
That saga highlights the cultural dynamic between AI labs and the community perfectly. Le Chaton Fat translates roughly to the fat kitten, which became a meme predicting Mistral's next big
I
release.
remember seeing that everywhere.
Yes, and on June 16th, Mistral CEO Arthur Mensch publicly winked at this meme online by correcting the grammar to Le Gros Chaton.
It definitely signals that the market is waiting with bated breath for Mistral's next major model moment. But focusing back on the technology, what is the core takeaway for the listener regarding this release?
This release proves Mistral's dominance in developing open, highly capable, infrastructure-friendly models. This specific approach makes U.S. frontier labs look decidedly closed and expensive by comparison. By deploying an open model that actually finds real, previously unknown GitHub bugs autonomously, the entire value proposition of open source AI is shifting.
I see.
We are moving far away from mere benchmark theater, where models just compete on standardized tests to get good headlines, and stepping into serious software supply chain gravity. Finding real vulnerabilities means open models are now actively securing the fundamental code that runs our global infrastructure.
So if we are mapping and verifying the fundamental logic of our digital world, the next logical step is attempting to rewrite the blueprints of the physical world. I will hand the floor over to cover today's massive updates in physical science and biology.
We will begin with a stunning step forward from scientists at the University of Minnesota who have created what they call Spud Cell. This is a synthetic cell assembled entirely from lifeless laboratory chemicals.
Wait, lifeless chemicals?
Totally lifeless. They did not take an existing cell and modify it. They built the molecular machinery from scratch. This synthetic entity mimics a full cellular life cycle. It feeds on its environment, it replicates its own genome, it physically divides, and it successfully passes that genetic material on to future generations.
That is incredible.
While it serves as a stripped-down blueprint for life, aiming toward future iterations that will be fully self-sufficient, it represents a monumental leap in synthetic biology.
Hold on. I need to push back on the terminology here. You're saying they created an entity from lifeless chemicals, and it actively eats, divides, and passes on a genome. If we're assembling the literal blueprints of life from scratch, at what point does a blueprint officially become alive? I mean, that spud cell development seems to completely blur the line between a biological machine and an actual living organism.
The distinction currently hinges on true self-sufficiency. Spud cell requires a highly controlled laboratory environment and specific chemical interventions to survive and complete its cycle. A fully living organism can adapt, scavenge, and maintain homeostasis independently in unpredictable environments. However, your point is exactly why this research is profound.
Got it.
We are watching the transition from chemistry to biology happen in real time on a lab bench. Moving to neurotechnology, Neuralink has achieved a massive surgical milestone by deleting the directomy. During conventional brain surgery, neurosurgeons have to cut through the brain's tough protective membrane, known as the duramater, to implant devices or access tissue.
Which the duramater is essentially the brain's heavy-duty security blanket. Cutting it introduces significant trauma, risk of infection, and spinal fluid leaks.
Exactly. In a world first, Neuralink successfully threaded their hair-thin electrodes directly through the intact dura in a human participant. They eliminated the need for a scalpel incision entirely. By pushing the electrodes seamlessly through that protective layer, they removed a major surgical risk and cleared a critical path to scaling this brain-computer interface technology to a much wider patient population.
That is a huge roadblock removed.
Absolutely. And in the biotech space, a startup called Conception has generated the first early human egg cells grown entirely from stem cells. The process is remarkable. Starting with just a simple blood sample from a patient, they reprogrammed those blood cells into stem cells. They then used those stem cells to grow miniature laboratory ovaries.
Wait, miniature ovaries from a blood draw?
Yes. And these lab-grown ovaries successfully produced early-stage human eggs.
The implications of taking a routine blood draw and transforming it into functional ovarian tissue are difficult to overstate.
The next immediate milestone for Conception is developing those early-stage eggs into mature fertilization-ready eggs. If successful, this breakthrough could eventually allow anyone to have biological children, completely regardless of age or their current fertility status. It functionally rewrites the biological clock. Finally, researchers at ETH Zurich have introduced the Fourier pixel. Traditional pixels on your smartphone or monitor are purely output devices. They only emit light. The Fourier pixel acts as both an input and an output simultaneously.
So it looks back at you.
It uses nanometer scale sculpted surfaces to emit and capture light at the exact same time. It gives hardware engineers total control over the brightness, the phase, and the polarization of light at the microscopic level.
To make that tangible for you listening, imagine the surface of this pixel not as a flat screen, but as a microscopic mountain range. As light hits those tiny nanometer-scale peaks and valleys, the physical shape actually bends the light wave. That alters the phase, which is the timing of the wave, and the polarization, which is the direction the wave is traveling.
That is a great way to picture it.
It acts like a microscopic two-way mirror. It could fundamentally change how everyday devices are engineered, turning every display you look at into a highly advanced sensor.
The potential use cases for the Fourier pixel are transformative. Because it can capture light while emitting it, you could build screens that double as high-resolution cameras without needing a separate lens. Controlling phase and polarization also unlocks advanced holographic displays that project true 3D images.
Fascinating.
And it creates entirely new methods for secure quantum communication directly through standard screen interfaces.
So while lab-grown cells and direct brain interfaces represent our long-term future, there are powerful tools you can leverage to boost your workflow today. Let us examine the 6 trending AI tools you need to know about and look at exactly how you can implement them. First is Acti, an agentic keyboard for mobile commands and search.
The keyboard.
Yes, instead of constantly switching between a browser, a notes app, and a calculator, you can bypass opening individual apps entirely. You can run complex, agent-driven searches straight from your phone's default keyboard, pulling research or executing commands while you are in the middle of typing an email.
Oh, that saves so much context switching.
Second is context.dev. This provides one single API to scrape, enrich, and extract data from the internet. If you are tracking industry news or competitor pricing, you can build a custom real-time research feed without needing to write or maintain any messy Python web scraping scripts.
Finally, no more broken scraper scripts.
You simply point the API at the targets, and it delivers clean, enriched data. Third is Cursor for iOS, allowing you to build with coding agents from anywhere. You can literally be sitting on a train during your commute, pull out your phone, and start debugging or deploying code alongside your AI assistant.
It brings desktop-level development environments to mobile.
Fourth is Glaze by Raycast, which lets you create your own Mac apps just by chatting with an AI.
Wow.
You type a few sentences describing what you need, perhaps a specialized clock that tracks 3 different client time zones and integrates with your calendar, and it instantly generates a custom desktop widget perfectly tailored to your specific daily workflow.
That level of personalization is amazing.
Fifth is Agent Mode by Receipter AI. This is a bookkeeping assistant running end-to-end receipt workflows. It fully automates your expense reports. It reads the receipts, categorizes the spending, and reconciles the data, ensuring you never have to manually enter a crumpled coffee receipt into a spreadsheet again.
The dream for anyone doing their own accounting.
Finally, Spira for product hunt makers offers social media growth agents. Launching a product is exhausting. Spira keeps your launch momentum going automatically across social channels, engaging with users and posting updates, while you stay focused on actually building and refining the product itself.
The unifying theme across all these updates is incredible practical mobility. Tools like Cursor for iOS and Acti demonstrate that high-level agentic workflows are finally moving off the desktop. They are moving directly into your pocket, turning your mobile devices from simple consumption screens into true autonomous execution engines.
Very true.
You are no longer just looking at data on your phone. You are deploying agents to work for you while you walk down the street.
The scope of today's deep dive has been incredible. Moving from Mistral democratizing complex mathematical proofs and autonomous bug hunting, to scientists creating lab-grown cells, and hardware engineers building two-way pixels that can see you while you look at them. It leaves us with a fascinating question to consider.
Oh.
If an open-source AI model can autonomously spot unknown GitHub bugs today, and scientists are assembling the literal blueprints of life from scratch in a laboratory, how long is it until we see open-source biology models? Imagine a future where discovering a new cellular structure is as collaborative as patching a piece of code.
The pace of innovation we are tracking across both digital and biological domains is truly unprecedented. The boundaries between software code and biological blueprints are dissolving faster than anyone predicted.
Be sure to follow and share the show so you never miss a deep dive into these rapidly evolving technologies. See you in the next episode.